Welcome back to differential equations. In this video, we're going to be talking about phase lines. Phase lines are closely related to direction fields. The way I like to think about a phase line is actually as a simplification of a direction field. Let me get my head out of the way and show you what I mean. An autonomous first-order ordinary differential equation is a differential equation which can be written in the form y prime equals f of y for some function f. Compare this to the differential equations for whom we were studying the direction field. Instead of having both x and y showing up on the right-hand side, now we have only y. I could put x there, right? A function of x and y that actually only includes y and not x is still a function of x and y. But specifically, having no x allows us to simplify things greatly. Instead of having to look across the xy plane at every possible point, no matter what x value you are looking at, things are going to work the same. So if you think about the coordinate plane, and just think about all of the vertical lines. I'm going to draw a few representative, but think about literally all of them. If you figure out a point at some height on the line, and you use that to calculate the slope, it will be the same at every single point on that horizontal line. So we don't need to look at the entire xy plane anymore. We can collapse this down and just look at the y-axis. And everywhere else going horizontally is going to behave in exactly the same way. I'm going to go ahead and jump in with a fairly complicated example. Let's look at the function y prime equals y to the fourth minus y squared. Now I know that this is an autonomous equation. I was able to isolate y prime, and there is no x anywhere in the equation. That's the first important step. The second important step is to start trying to think about the phase line. And so we're going to have some points that are going to have a positive slope. We're going to have some points that have a negative slope. We're going to have some points that have zero slope, and we're probably not going to have any undefined slopes in this particular case. But we know that the only way to go from positive to negative or from negative to positive is to either go through zero or be undefined at some point in the middle. There's no other way to make that jump. And so we want to look for the critical values, the places where y prime is equal to zero. In this case, that means that y to the fourth minus y squared is equal to 0. We can solve this equation by factoring. There's a common factor of y squared that I can factor out. And when I do, it leaves behind y squared minus 1. I think it makes a little more clean of a solution to separate now and say that either y squared is equal to 0 or y squared minus 1 is equal to 0. If y squared is equal to 0, then y itself is 0. If y squared minus 1 is equal to 0, then either y plus 1 or y minus 1 is equal to 0, just factoring further. All right, so we get three solutions: y equals 0, y equals 1, and y equals negative 1. And taking those solutions, I'm going to draw them onto a phase line. Let's try to scroll this a little bit more neatly so that I can get my original function and some space. That looks a little bit better. All right, so let's go ahead and draw a y-axis. Let's go ahead and label 0, 1, and negative 1. And yes, I'm making sure that I have plenty of space. And then I'm going to draw an open circle at each of those 3 points. We're going to decorate those circles, but for right now, I'm going to leave them as open circles. And doing the thing that you do so often in calculus when you look at critical values, these divide the y-axis into a couple of ranges. I want to plug in a value in each of those ranges and see what happens. All right, so something bigger than 1, like maybe 2. Well, 2 to the 4th is 16. 2 squared is 4. 16 minus 4 is 12. But the thing that matters is that that's positive. And so the function is going to be increasing in the space up here. If I plug in something between 0 and 1, like 1/2, I'm going to get 1/16 minus 1/4, which is negative, let's see, yeah, negative 3/4? No, that doesn't make any sense. 1/16 minus 1/4 is 1/16 minus 4/16, which is negative 3/16. But really, the only thing that matters is that it's negative. And if y prime is negative, that means that the function is decreasing. So I'm going to mark in that the function is decreasing in this range. If I try a negative value like negative 1/2, I actually get the same result, negative 3/16. So the function is still decreasing in this range. And if I try something very small and negative, like negative 2, that's going to give me negative 2 to the 4th is positive 16. Negative 2 squared is positive 4. So the difference there is positive 12. Y prime is positive, so the function is increasing. All right. So now I have decorated my phase line just a little bit. I'm going to move my phase line down so that I have some space to work next to it now that I don't need the original equation anymore. All right, so now that I have this, I'm going to draw out a coordinate plane. So I've got my t-axis, I've got my y-axis, and I've got my positive 1, my negative 1. 0 is pretty easy. And I can try to start drawing in some information here. Well, if I start somewhere above 1, the rule says that I'm going to be increasing. So it's going to look like something like that. At 1 itself, y prime is 0. Y prime is always 0 when y is 1. And so that's going to give me a line that looks like that. Y prime is always 0 when y is equal to 0. So there's a solution that looks like that, and a solution that looks like that at -1 as well. All right. So always increasing is fairly straightforward up here at the top. Decreasing between 1 and 0. So it is decreasing between these. It's going to start up here, it's going to go down there, but it's not going to go past here because right here is where the function is 0. So I have to try to come up with some way of making that work. I need to be decreasing and I need to mellow out before I get there. I guess that's going to be some sort of an asymptote. So solutions that look kind of something like that. And the same thing is going to happen in this range. And then kind of the opposite down here at the bottom. I am increasing, but I have to stop here at -1 because at -1, my slope is 0. So I know I have to come up and go towards an asymptote. All right, so I'm going to have curves that look kind of something like that. So those three critical values really drive the solution. The critical value at y equals 1 pushes the result away the whole time. We can describe that as an unstable node. If you are at 1 exactly, you stay at 1 and you stay at 1 forever, which is really nice. If you move the slightest bit away from 1, all of a sudden you're gone, and I'm incredibly blurry. There we go, less blurry. All right. Think about that like trying to balance a pen on your fingertips. Right? I can keep it there for, sorry about that. I can keep it there for a second, maybe a little bit longer, maybe not quite that long, but pretty quickly it's going to tip over. Right? It's unstable. It's a balance point that doesn't work very well. Down here at the bottom, when y is -1, that's a little bit more clean. All of the values are coming down towards it. If you are at -1, you stay at -1 forever. If something pushes you and you end up a little bit off of -1, well, you're going to fall right back into -1. All right, I think of that kind of as the hanging balance. So if I hold the pen from the top, well, that's a lot easier. If I push the pen, it goes right back to where it is. It's stable like that. And then the last point here at y equals 0, we call semi-stable, where it kind of has both behaviors. From 0, if I push up a little bit, it gets pushed right back down. From 0, if I push down a little bit, it gets pushed all the way down to -1. So it's stable in one direction, but not in the other. And the last thing I want to do is come over here to my phase line. And whenever we have a stable node, we draw the circles filled in. Whenever we have a semi-stable node, I've seen a couple of different markings for that. My personal favorite is to draw the node with a plus or an X in it, whichever is more readable. And then an unstable node stays open as it was drawn in the first place. So by thinking about the stability here, by thinking about the critical value and where the function is increasing or decreasing, we can get a lot of information about the behavior of the system right there. One of the classic applications of the phase line comes in population dynamics. Let capital P of t be the population of rabbits in a field at time t. Well, I know that the rate of change of the population has to be proportional to the population. Right? If you've not seen that symbol before, that's proportional to. The idea of proportional should be familiar to you. Sometimes um, actually writing a proportion symbol comes up, sometimes it does not. Right? I know the more rabbits there are, the more rabbits there are to breed, and the more new rabbits are going to be born in any given period of time. So the population is going to depend, or the rate of change of population is going to be proportional to the population. But I also know that there has to be some carrying capacity. Call that carrying capacity K. So that the rate of change of population is also going to be proportional to the difference between the carrying capacity and the population. Right? Another way to think about this, there's only so much field and there's only so much grass in the field. If your population of rabbits is so large that there's nowhere for the new rabbits to sit because the rabbits have filled the field, well, the new rabbits aren't going to survive very long and you're going to start seeing rabbits dying off. If there are so many rabbits that they are eating the grass faster than it grows, you're going to run into trouble because the rabbits aren't going to be able to eat, they aren't going to be able to survive, the rabbits are going to start dying off. If you are very far away from the carrying capacity, then that's not going to be much of a problem and you're going to see the population growth grow very quickly. If you are very close to the carrying capacity, you're going to see some trouble and the population isn't going to grow anymore. Um, the difference is zero, the rate of change is going to be zero. If your population exceeds the carrying capacity, then rabbits are going to die off faster than they can be born. This is going to be negative, and you're going to have a decreasing population. So it makes sense mathematically in the model. Um, in order to do things from the mathematics perspective, Having that extra constant in the problem is annoying. So let's set k equal to 1, and we're going to measure p as the percent of carrying capacity. So instead of the number of rabbits, what percent of the maximum number of rabbits do we currently have in the field? And so now we have that my differential equation, dp dt, is proportional to p, and it's proportional to 1 minus p. And in proportionality, being proportional to things means that there is some constant so that we have equals that constant times the stuff on the right-hand side. Right? Now we get to do another thing that mathematicians love and scientists look at and say, what the heck are you doing? If I was a biologist and actually studying rabbits in the field, it would be very important to me that I'm measuring time in hours or days or weeks or months or something that makes sense. But I'm not a biologist in the field, I'm a mathematician. And as a mathematician, I am very happy to say, well, let's pick the time interval that makes this rate of proportionality equal to 1. Because the rate at which the population is growing will change depending on how you are measuring time. The population may be growing at a rate of 1% per day. What I'm looking for is the rate at which the population is growing by the product of the population times the distance from the carrying capacity, right? So my time interval is how long does it take for that many new rabbits to be born. And whatever that time interval is the unit of time that I'm using. It makes the math a lot easier. It makes the science a lot harder. But I'm a mathematician, not a scientist today, so I'm happy to do that. All right, so I've got dp dt. Let's do this in white again. I've got dp dt is equal to p times 1 minus p. This is known as the logistic equation. It shows up in several different aspects, and putting constants in and making a mess of things is certainly a thing we can do. I'm not that worried about it for right now. What I'm worried about is noticing that this is an autonomous differential equation. It involves p, it does not involve t. And because it is an autonomous differential equation, I can set up a phase line, I can find the critical values. I can plot those critical values. And I can figure out what's going on between the critical values. If I pick a value for p less than 0, then I'm going to get a negative number times a positive number, which is negative. Right? What that means as far as our population goes, I have absolutely no idea. How do you have a negative population? That's nonsense, but that's okay. Again, we're doing the math, and it's up to the scientists to do the interpretation later on. If I'm looking somewhere between 0 and 1, something like 1/2, well, 1/2 is positive. 1 minus 1/2 is also positive. And positive times positive is positive, which means that the population is increasing here. And then if I pick something bigger than 1, like 2, I've got 2, which is positive, 1 minus 2 is negative 1, which is negative, and positive times negative is negative. So my population is decreasing up here. And those two should make sense. If your population is below the carrying capacity, which is what's happening here, right, somewhere between, between 0, so the population exists, and 1, which is the carrying capacity, when your population is in there, your population is going to grow. If you're up here, your population is bigger than the carrying capacity, and your population is going to shrink. But no matter which way you're going to kind of stabilize at 1, which is the carrying capacity. Right? So at 1, we have a stable node. When the population of rabbits is at 100% of the carrying capacity. If something causes the population to fall a little bit, someone comes or a wolf comes and eats a couple of rabbits. Well, the population is going to quickly rebound. More rabbits are going to survive their childhood, get to adulthood, and the population will grow. If the population is growing and a number of rabbits are born, taking you above 100% of the carrying capacity, well, there's not going to be enough grass for all of those rabbits to eat. They aren't all going to survive, and the population is going to drop back down. It's very stable once it gets there. 0, on the other hand, is an unstable node. If there are no rabbits, there will continue to be no rabbits. Rabbits don't spontaneously exist. But if you introduce a pregnant female rabbit and you allow it to thrive, it will be fruitful and multiply, and eventually the population will grow. Again, the whole idea down here of what happens when the population is below 0, I have no idea. That doesn't seem to fit the physical model in any way, shape, or form, but it is still mathematically possible, so we can talk about it. We have talked about it, and yay, I guess, or whatever. I don't know. All right. Now that we have this basic model established, I'd like you to do the next step. The last time we looked at a phase line, I then drew coordinate axes, and I sketched in a few representative curves to model the trajectories. I would like you to do that for this one. Draw a coordinate plane, so we're going to have a t-axis, and we're going to have a p-axis, and draw in a few representative curves of what the population is going to look like in that two-dimensional space. All right, see what you can do with that, and I'll see you in the next video.